So the next speaker is Roberto Bondesan, and he will speak us about learning lattice quantum field theories from equivariant continuous flows. Thank you.
Yes, thank you very much. And thank you very much for the invitation. It's a great pleasure to be here among many illustrious colleagues. So this is the outline of my talk. The first part will be motivating the problem we're looking at, and which can be summarized really as how to apply machine learning to study statistical field theories. In the second part, I will talk about the technical innovation of our work, which is coming up with a neural network architecture, which we call equivariant neural ODE, which I will introduce to solve this problem. And then I will present some proof of principle results for the 5 to the 4 theory. So first of all, a little bit of motivation, right? So as we also learned in the previous talk, machine learning has been revolutionizing domains like computer vision and natural language processing. For fun, I took here one of these latest models, which is a diffusion model, which is basically a neural network that allows you to sample the probability distribution of natural images conditioned on some text. So here I just inputted a painting of a group of physicists celebrating a birthday in Trieste, and there you see what kind of picture the neural network hallucinates. So these models are fun to work with, and they have, of course, a lot of impact in the industry. But what I'm trying to ask today is, can we use machine learning to solve problems in physics we care about, like statistical field theories? So more precisely, the problem I would like to look at is the following, which is a central problem in the field, which is how to sample configurations of a field phi from a probability distribution P of phi. To fix ideas, you can think about that phi lives on the square lattice where the value at vertex x is called phi of x. So the standard approach to such a question is to use a Markov chain Monte Carlo. So here is a cartoon, like if we have just a two-dimensional field, and so that the distribution is two-dimensional on this plane. In blue, there is the high probability region, and the Markov chain, Monte Carlo, creates a Markov chain that starts somewhere in this space, and then, as you see, gets attracted to the high probability region. And so to sample, you can just collect samples along this way. However, there are challenges to this very general algorithm. In particular, the samples you get are correlated. And this, of course, is a problem because it can lead to high variance of the estimated observables. Also, this is particularly challenging near the critical point. So this then motivates practitioner physicists to come up with sophisticated handcrafted algorithms for each new theory. And this can be time-consuming. And finally, every time you need to study observables for different lattice size or different coupling constants, you need to restart the Monte Carlo simulation from scratch. And this, again, can be computationally costly. So here I just sketch how machine learning can help solving this problem. So first of all, there is a very simple way, at least conceptually, to sample from a probability distribution if you know a map that maps an easy to sample distribution, for example, this blob here, which is a Gaussian blob, to your target distribution. So this gray sphere here is the space of probability distribution. And so what we need to do is to simply sample independently from a Gaussian and then push these two samples through our map, and then we get our samples according to P, and they are independent as we expect. So this is, of course, good, but the central question then is how to construct this map from a Gaussian to our target distribution. And that's where machine learning can help. We can, in fact, parameterize this map with a neural network. At initialization, when the weights of these neural networks are arbitrary or random, clearly we are not going to map a sample from P, but from another distribution Q, which looks different. But then we can devise an algorithm to simply minimize the distance in probability space between Q and P. And if we succeed to do this, then we have solved the problem. So here on the right, I just sketch a little bit more details of what I just said. So the main idea is to amortize the sampling of, the cost of sampling from a distribution by training a neural network. So the first sample indeed this random variable eta, which is a Gaussian. We pass it through a neural network, which is a flow in the probability space, f of theta, where theta is the learnable parameter of this neural network. And we obtain a new variable phi, which is distributed according to distribution Q. Then we compute a loss, which is here this scale divergence. You can see that when Q and P are equal, this loss is 0. So what we try to do is to minimize this loss and to with respect to theta. So this is all good, but sorry, in practice, we don't achieve 0 loss. So what we can do for a practical algorithm is to use a Q which has been trained to a desired convergence as a proposed distribution in a Metropolis Hastings algorithm, which accepts, rejects these proposals, and so guarantees that we sample from the correct distribution. So now a little bit more technical details about the way to construct this neural flow. So we use the method which is called the neural ordinal differential equations. The idea is that you have an ODE, which is written as follows: z dot equal to g theta z comma t, where the vector field G is neural, so it is given by a neural network with parameter theta. And the idea is that we just set the initial condition to this ODE to be z at time 0 equal to eta, which is our Gaussian random variable. And we expect that at time t equal to 1, say, we have our observable our field phi. And so the Q of phi that I mentioned in the previous slide is simply identified with a probability distribution of this z at time 1. And you can easily show that this probability distribution satisfies another ordinal differential equation of the following form, where the logarithm of p of z of t varies according to the divergence of the vector field G. So on the right, I sketch what this looks like in practice. Suppose that the target distribution is two concentric circles. In the middle, you see the time evolution of z, of the samples, right, starting from a Gaussian and then deforming to the correct one. And on the right, you see the log probability distribution, again, plotted to show that the probability from a Gaussian becomes these two circles. So this is all good, but the problem is that if you see here, we have a divergence of a vector field. And so this computation takes on squared time. And so if n now is the number of vertices in your lattice, for example, this constitutes a computational bottleneck because it doesn't allow us to go for very large n. So part of our innovation then is to come up with an architecture that allows us to have an efficient algorithm that scales linearly with the number of vertices. So here I sketch the parameterization that we came up with. So the x component of this vector field G is produced as follows. We take in a vector phi of fields and a time variable t. Then we produce what we call feature maps. So we compute a nonlinearity, which is here a sine of omega phi, and here sine of alpha t and cos alpha t. Then what we do is that we contract these features with the tensor W, and then this produces the value of our vector field. These parameters in red are learned. And the intuition here is that we are kind of doing a Fourier expansion of this quantity. That's why you get sine and cosine. However, what we are doing is that we are subsampling the components that we are keeping, and we are learning which frequencies are the most relevant to us. So this allows us to have indeed an efficient algorithm. And what we do next is actually to encode the symmetries of the problem on the model architecture. In fact, the target distribution P coming from a physical model has several symmetries. And in particular, here I show the symmetry under 90 degrees rotation of the square lattice. So G is the map that rotates the lattice by 90 degrees. So what you would like to do is that your proposed distribution Q has this symmetry for all values of the learnable parameters. So this is indeed the case which will allow you to have the fewest samples to learn from. and so the most efficient. And so to achieve this property, since our initial distribution of eta is a Gaussian, the only thing we need to do is to ensure that our flow F is actually equivariant, namely commutes with the action of the symmetry G. So in practice, in our parameterization, this means that the tensor W needs to commute with the square lattice symmetries. And since we're going to think about later as a scalar field theory with the Z2 symmetry, we already know that we need to remove the cosine from this expansion. That's why it didn't appear there. Okay, so in this way, we have come up with an efficient algorithm which encodes the symmetries of the problem. And then I'm just going to present some results with this model. So this figure captures the behavior of the effective sample size, the ESS, which is a measure of the independence of the samples that you produce. And you would like this to be high, ideally 100%, where all the samples are independent, as a function of the training time. So this is a training time on just a single GPU that you can have easily access to. And so here we do this training of the model for different values of the number of the system length, which is L. We study 5 to the 4th in 2D, so the size of the lattice is L squared. And you see that this is compared against the baseline, which is so-called the real MVP model. So I will not enter any detail here, but just to tell you that this was the previous state of the art in this field, namely when people try to apply machine learning for sampling from field theories. So you see here that, for example, for L equal 32, the previous model got a very bad ESS after training it to convergence, which was 1%. Instead, we get 91%. So that's a great improvement. And another thing that we show is that we can also transfer across system sizes L. Namely, you can, so this is the data that is shown in the dashed lines. Namely, if you start training a model for a given value of L, for example, L equal 20, and then you transfer it. So you just transfer the weight to a different size, which is L equal 32 with some procedure, the model starts already at a pretty high ESS. So this allows you to reduce the training time even further. And on the right, I also show a pretty interesting variation of this model, namely where we condition the samples on the coupling constants lambda. And so there is a very simple-minded way to do it. Namely, again, we take our coupling constant, we embed it in some feature space, and then we add an extra leg to our tensor W. So this allows us, with the same training cost of training a model for a fixed lambda, in fact, to train a model over a range of lambdas. And so this, in turn, allows one to produce, studies of the susceptibility, for example, chi, as a function of a range of values of lambda very, very quickly. And so, for example, you can easily show that, for example, these curves collapse for a given scaling function, and you can recover the Ising as points. Okay, so this leads me to the conclusion of my talk. So I try to motivate the fact that machine learning can accelerate the sampling of statistical field theories by amortizing the cost via training. And so the main contributions that we proposed in our work are, first of all, reaching a new state of the art in this field using a new equivariant neural OD architecture. Then we showed that we can also transfer the model that is trained across lattice sizes to reduce the training time, and also that we can condition the model on the coupling constant, which gives an efficient way to study the phase transitions. So current work in progress aims at extending these ideas to more interesting theories, and in particular to long-standing problems like QCD. So here's a couple of references. And also I would like to thank my collaborators, Mathis, P, Corrado, and Miranda. And now I would like to wish Sergio happy birthday and thank him very much for his support and contribution to my career. We have not kept in touch in the latest few years, but I like to think that I learned from him several things, and in particular, the open-mindedness to new topics, new fields, which allowed me to explore things beyond physics, machine learning, and so on. So thank you very much, Sergio, and thanks everyone for your attention.
Thank you very much, Roberto.
Sure.
Are there any questions? If not, let us thank Roberto again.
Thank you.